Okay, so number 12 and number 13 come from chapter 8, so they're not required for those of you in this semester of spring 2020. Okay, so if you're interested or you're looking at this in June, what would be the integral of this particular exponential function? So what I would first of all do is write this as two separate pieces. So 10e to the power of 3x on e to the power of 6x minus 2e to the 4x on e to the power of 6x, all in terms of x. And then that would reduce to equaling to 10 e to the power of 3x minus 6x would be negative 3x dx. I'm going to do these as two separate integrals. 2 e to the power of 4 minus 6 is negative 2x dx. And then, in fact, I could have put those 10s and 2s out the front. That would have been smart. So put the 10 out and integrate e to the power of negative 3x dx minus 2 integral e to the negative 2x dx. And this actually doesn't require me to do the substitution rule because I put this little bubble out here for us. The antiderivative of e to the kx is 1 on k e to the power of kx. So we're just going to use that little antiderivative rule right there. In this case, the first one, the k value is negative 3, and the second one, the k value is negative 2. So this is going to be 10 times the antiderivative of e to the negative 3x is e to the negative 3x. The antiderivative of e is the same, divided by that coefficient on x, so negative 3. There's a subtract 2 times the same thing for the second one. We have e to the negative 2x divided by the coefficient on that x is negative 2, and then plus c, and then we just tidy it up. That's it. So this would be equal to negative 10 on 3 e to the power of negative 3x. Negative 2 divided by negative 2 is plus 1, so plus e to the power of negative 2x plus c. Which you could write if you wished with the e's down below because they have negative exponents. So I could have written it as negative 10 on 3e to the 3x plus 1 on e to the 2x plus c, but it's up to you. And then this second one, again, this one we have more going on. He has a product 4x squared e to the x cubed. Remember, products, we're not undoing the product rule on this integration. It's not true, okay? We're undoing the chain rule. So in trig functions, we usually use the argument as our u. In an exponential function, we're actually going to end up using the exponent. So this one's a little bit more complicated than 12. This one does require me to use the substitution rule. Okay, so in this case, I'm going to let u equal the exponent on the e, on the exponential function. So let u equal x cubed. And when you take the derivative of that, du dx is equal to 3x squared. So you can see that x squared piece is matching. That's going to be good for us because when we substitute, those x squareds should cancel for us. And then we don't care if we're left over with numbers. They're just going to go out front. Okay. So then rearrange this, we would get that dx is equal to du on 3x squared. Now we can do our substitution. Okay, so secondly, I'm going to integrate 4x squared. We didn't substitute that part. E to the power of x cubed. Now that's my u. And then I have that in terms of du on 3x squared. Now my x squareds can cancel, and it leaves me with the constant of 4/3, which I'm going to put in front of my integral sign, and then I'm integrating e to the power of u du. And the antiderivative of e to the u is e to the u. It's very easy, the e guy. So this would just be 4/3 e to the power of u plus c. But of course, we then need to substitute in who was u to start with. So this would be 4/3 e to the power of x cubed plus C. And there. So there was a couple of examples for exponential functions. And again, it's not necessary for this semester for you guys to learn those ones, but just those of you who are curious. All right, 9.1 is done. I'll see you